Hi everyone, I'm Professor Bergesser, and in this video we're going to be expanding our definition for energy conservation to include non-conservative forces. And in particular we'll be focusing on dissipative forces, forces that cause the loss of energy to a system. Now just to remind you, we have these conservative forces that actually represent a large number of the forces that we've considered, things like the spring force, gravity, even the tension force, where the energy change, the change in kinetic energy, which is the work done on the system, doesn't depend on the path that an object takes as it moves around the system. It only depends on the endpoints. So if we're going between point A and B on this diagram, the work done following path 1 is exactly the same as the work done following path 2, and it only depends on the relative placements of point A and B. Now we call forces that behave like this conservative forces because if you take the paths all the way back to its original point, we should end up with exactly the same kinetic energy that we started off with. So somehow the energy that is expended or stored by work is preserved in the force interaction itself. And so it's conserved in some way, and so this is why we call these conservative forces. And because of this definition, we can then define a couple new quantities. One is the potential energy of a system, and that is just the negative of the work done by these conservative forces. And that added together with the kinetic energy gives us the total mechanical energy. And what we find is that when we have only conservative forces, that sum of kinetic plus potential energy is conserved. It's constant with time. And so it's a number that we can just write down, and then we know that's true throughout the entire interaction, no matter how complicated it might be. So to see an example of a non-conservative force in action, let's take the case where I'm sliding an office chair from one end of an office to another. And so that's represented by this two-dimensional plot where I've plotted the x and y coordinates of my office, and I'm starting from an initial point and sliding the chair to a final point. In this case, the friction force is the force that we're interested in because it's the one that's acting in the opposite direction of motion. And I can quantify this just simply as the coefficient of kinetic friction times the normal force between the floor and the chair itself. And let's just assume that this is a constant magnitude of about 5 newtons. And of course it points in the opposite direction of motion, so I've indicated that by the minus v here. So this combination indicates the direction of the motion. All right, so if I slide this from point A to point B, then this is just a constant work done by the friction force, and I can calculate that as minus the magnitude of the friction force times that displacement. It's minus, again, because we're moving against the direction of motion. We have a force pointing in the opposite direction of motion, so it's going to do a negative work. And now, so that length is 5.7 meters, which is just the hypotenuse of a triangle. That's 4 meters on a side. We multiply that by the 5 newtons of friction, and we get a total work of minus 29 joules. And again, that's the change in the kinetic energy. So if we give this chair a good push at the beginning, by the time it reaches its final destination, it will have slowed down, and that amount of slowing down will correspond to 29 joules of kinetic energy lost. All right, now let's consider a second path where we slide this chair off to a corner and let it bounce up to the opposite direction, and so we're following a slightly longer path. Again, because the friction force is always acting against the motion, we can break down the work in this path by the work done along each of these different lengths, and that's just the friction force times the displacement, again negative because it's acting in the opposite direction. So quantitatively, that's going to be 5 newtons times the sum of 4 meters and 4 meters for a total of minus 40 joules. Now notice that in this case, unlike our conservative forces, the energy that's changed between these two paths is different. We've lost more kinetic energy by following the indirect path than we did by following the direct path. So this is clearly not a conservative force because it doesn't satisfy that constraint that you have to have a path-independent work. Now, it becomes even more important when we consider the case where we'll do a closed loop. We'll start with the chair at one corner, we'll swing it out to the corner and let it bounce back to where it started. In that case, we're going a full closed loop, and if it was a conservative force, we'd expect to have the same kinetic energy at the end. But of course, in all three of these paths, we're losing energy to friction, and that's going to be the sum of the different displacements times the friction force. When we add all these numbers together, we get a total of 69 joules of kinetic energy lost. And that is certainly not 0 joules, which would be the case for conservative force. So in this friction force, in this non-conservative case, we find that there is a net loss of kinetic energy because if I come back to the same place, we don't have the same kinetic energy as we started from. So since non-conservative forces have a path-dependent work term, we have to take into account the actual work done by those forces. And we can't assign a potential energy for something like friction because it's not something that will be stored. We actually lose that energy as we move through the system. So we have to go back to our work energy theorem, and we can break apart our force terms and our work terms into non-conservative and conservative forces. And when we do that, we can see that the change in kinetic energy, being the sum of these two work terms, work from non-conservative and work from conservative forces, is just equal to minus the change in potential energy plus that work done from non-conservative forces. If we group terms exactly the same way we did before, we find that the change in the total mechanical energy, which is the sum of kinetic and potential energies, is now equal to that non-conservative work, which again is just the integral of the force along the path. Now notice that for dissipative forces, that work term is going to be negative. It's not written with a minus sign here, but in general, because dissipative forces tend to have the forces acting in the opposite direction of motion, that Fnc dot delta r is going to give us a minus sign because those vectors are pointed in the opposite direction. Now you may ask, where does all this energy go? If we're losing, in the example that we saw, 69 joules of energy, where did it actually go? Did we actually destroy energy in this process? Well, of course no, because one of the things that we learned about energy is that energy is neither created or destroyed. It's simply transformed into other forms. And in particular, when we talk about friction, the relative motion of the surfaces, that process is actually transforming the kinetic energy of the objects into another form called heat energy. And that heat energy is really just the random motion of the molecules. So we've transferred a bulk motion to random oscillations of the molecules and the materials. And that random oscillation, that heat, then is turned into radiative energy, and that radiative energy is radiated out, particularly in the infrared. So the images you see here of someone braking on their bicycle wheel, you can see in the top image that there is this warm streak that's coming out from our infrared light. That is the radiation of infrared energy, light energy, from a hot region on the ground, and that hot region is hot because of the transfer of kinetic energy into heat energy on the ground. And you can also see that even on the bicycle wheel, the tire where the sliding occurred is also radiating infrared radiation. And that infrared radiation comes from the heat, and the heat again comes from the friction. Now, other forms of dissipative energy include sound and vibration, or if you're screeching your tires, that sound is a transfer of kinetic energy into the pressure energy of the air being pushed back and forth. And you can also have vibration in the materials that are rubbing against each other. All of these forms of energy are known as dissipative forms in the sense that they actually radiate energy away. The energy is actually being transferred from the site at which this transformation occurred out into the environment. And of course, that's why we can see the infrared radiation in this picture, because that energy of radiation is coming from that spot into the camera. It's radiating away. In all these cases, we're actually losing energy from our system of bicycle and floor because of this dissipative form of energy. So now we can go back to our process of solving an energy problem, and we can look at this now more generally as any kind of problem that involves both conservative and non-conservative forces. It's just a little bit of a change to our main process. We start with exactly the same steps we had before. We write down the things that we know and the things that we're solving for. We look at what type of problem this is, and we make some predictions about the motion. And we break down the system into its key parts and look at force diagrams for each of those parts written in an inertial coordinate system. Now at this point, as we did before, we're going to break down some key events, an initial, a final event, maybe a point where things change, and write down the kinetic and potential energies at each of those points. But then we're also going to compute the work done by non-conservative forces between those events. So for example, in our sliding the chair across the office, we computed the work done between the initial position and the final position explicitly as the work done by non-conservative forces. Then we go back to our full definition for the change of energy, which is the change in kinetic plus potential energy is equal to the work from the non-conservative forces. All right, so instead of saying that equal to 0 when we had pure energy conservation for just conservative forces, we now set that change of energy to whatever the work done by the non-conservative force is. And at that point we can solve for our unknowns. And of course, the most important step is to check our answers for their units and also to consider some extreme cases. So you will see some examples of how to follow this procedure in the next few videos, but keep in mind that this is very similar to our Newtonian practice. We're just adding in a little bit here to take into account both conservative and non-conservative energies. So to summarize, we have a work term that we can compute for non-conservative forces, and that work term is path dependent. It's very different from our conservative forces where it only depends on the endpoints. In this case, we have to explicitly compute the energy that is added or gained from this non-conservative force along the path. And if those forces are dissipative forces such as friction or viscosity, which transform kinetic energy into radiative forms like light and heat and vibration, well, that energy is then lost to the system. And so the total energy of our system is going to go down in the presence of these non-conservative forces. And so when we want to actually compute the total mechanical energy and how that total mechanical energy changes with time, we have to actually take into account those non-conservative forces. And that's simply written as the change in the total mechanical energy is equal to the work done from non-conservative forces, and that's just the integral of the force dot the path or dot the displacement.